Welcome to Lecture 6, Transmission Line Part 1. So we will be doing transmission lines in two parts because there is few grounds to cover. Now, transmission lines are used to transfer the energy, or it actually stores the electric and magnetic energy distributed in space, and they alternate between them. Electric and magnetic energy, they alternate between them, and that's how they can transfer energy from one place to other. These are a few samples of transmission lines. The first one is a two-wire line shown here. So this is something that we see in the twin line pair. So one line would be the signal, the other line would be the ground in the normal sense. So that together can carry the signal along the line from one place, which we call the source here, to the load. Now, there's other ways of transmitting the signal. So this is two-wire line, as we said before. That you see even in your final project-wise design, or even in your labs. So you have a ground plane and you have a substrate, and then you have the microstrip. So the signal travels, so the energy is stored in this medium and in the surroundings. The field of the electric field changes between the microstrip line and the ground. So the electric field goes like that. So that's how the energy is stored, and that's converted to that's stored as electric energy, get converted to magnetic energy, and then converted to electric energy. So it alternates between them, and then when you have potential difference, it allows you to transmit a signal from one end to the other. Now the microstrip lines can have different forms. Well, microstrip can have only one form, but there's other types of transmission lines. If you say that you can have a ground, and you have a ground, and you can have the signal in the middle. So the field is constrained between the signal path and the ground path. So that's called the strip line. Or you can have a differential line where you don't have a ground. So it could be actually one of the positive signal, while the other would be negative signal. So it's very similar to the two-wire line, but implemented on a with two strips. So this microstrip is what we talked about. Coplanar is the signal path here, signal traveling strip line here, and then these are ground, and that's ground. So this E field is from the signal to the ground, and then the wave. So this is only this is a side cut or cross section of this microstrip or whatever the transmission line. Then you can also have a differential line. Instead of being in the substrate, it could be on the substrate. So it has two mediums. One is the substrate medium, one is the air medium. So that's another type of transmission line. So that's all substrate based transmission lines. So we covered a two-wire line, stripped above ground line, no microstrip line. And then you could have a coaxial cable, which you would see the center conductor is the signal and the outer conductor is the ground. So the field goes from center conductor to the ground, and the field is confined. So there's not much leakage outside. Now, if you see in addition in things like this, you can have a leakage, because when you have the fields coming from the microstrip to the ground, you have to go, you extend your fields to the air as well. So you can have certain leakage, and there can be certain, it results in a certain loss as well. Now the coaxial cables you may have seen in the television, from the antenna to the TV, in the analog lines. Now with IPTVs you won't have this because it's all digital, and any other communication systems most likely to have types of coaxial cables. So this basically we are trying to learn how the transmission works from one end to the other, and how can we derive certain parameters um, using the transmission lines. So the wave propagation. So as I said before, if you can have a source, that's a voltage source, and you can have impedance associated with that source. And when you have a transmission line that has an impedance, so impedance is something that you might be somewhat familiar, or you can so that's the resistance that it provides. It's not exactly a resistance. The impedance comprises of real part and imaginary part. So it can be resistive, it can be reactive. Now that impedance of transmission line will have a certain impedance, and then it will deliver that signal or the power to a load. Now there's certain things that we need to understand. If it's a RF wave, or radio frequency wave, or it will have a certain frequency, and with the frequency it will have a certain wavelength. Now from your preliminary courses, you know that wavelength is the time it takes to wavelength. So your voltage can start from some place and can come to so if it's a sinusoidal periodic wave, this is called the wavelength. Okay, now so there's this relationship between the wavelength and the frequency of the signal. It's got C equals F lambda. So from there we can say lambda equals C over F. So if you want to find the wavelength of a signal, you just need to know the C, which is the speed of light, and the frequency. This is in hertz meters per second, and then you get the lambda in meters. Now the same way, that's the wave propagation in the air, or like in a vacuum. So the air and vacuum, we treat them as similar. But when the wave propagates in a transmission medium, it cannot travel at the speed of light, which is c. So it will have a certain velocity for it to travel, and we call that the phase velocity, and it's called Vp. But the same relationship holds. So the wavelength in that medium we call the guided medium, because it's not air or vacuum, it's a guided medium, is equal to Vp divided by F. So instead of the speed of light c, we have the phase velocity. Now this Vp we can calculate in different ways. The one way to calculate that is Vp equals 1 over mu epsilon. Now mu is the permeability, the epsilon is permittivity. So those values are given. So in vacuum, epsilon is, we call it epsilon naught, permittivity of free space, and it's given by this number 8.854 times 10 to the power minus 12. Permeability is mu in vacuum or free space, we can say it's mu naught, and it's given by 4 pi times 10 to the power minus 7 Henry per meter. So if you know mu and epsilon, if you find mu epsilon product and divide by root square of that product, you will find that Vp is equal to the speed of light. So it will come very close to 2.99 10 to the power 8. Now, if you have if you are in a medium, your Vp would be 1 over mu epsilon square root. Now you need to find for that particular medium what is the effective permeability, what is the effective permittivity. So it might not be, it will not be the same as free space, it will be something different. So what happens, you most likely our permeabilities are same as the free space. So your mu would be same as mu naught. There's another parameter that we define, which we call epsilon r equals epsilon of epsilon naught. So this is a comparison parameter. So we call this a relative permittivity. We call this the relative permeability. So if you know if you know the relative permittivity, and then you know the permittivity of free space, then you can derive. So say for example, relative permittivity is 1.3 for a certain material, then its permittivity is epsilon divided by epsilon naught. So if you want to find that, its permittivity epsilon would be 1.3 times epsilon naught. So we only need to know the free space permittivity, then we can derive, and when we know the free space permittivity and the relative permittivity, which is epsilon r, then we can derive the permittivity of that medium. So in this case, it becomes 1.3 times 8.854 times 10 to the power minus 12. So the units remain the same because this doesn't have any other units. Now that way we can find permittivity of other materials, but there's a separate I guess a lecture in finding or measuring permeabilities of material. We are not going to do details on that. But what you need to remember, if you know relative permeability, you can find the permittivity and permeability of that material. You may have covered this content from a different course as well. Now, the other thing you need to remember is like when the signal travels, signal will always have a forward traveling wave, which we will follow up in the next couple of slides for sure. And when it hits a change, it's like it is similar to your light in the physics lessons you did. It goes from one medium to other, where the light or sound goes from one medium, say air, to water. It at the boundary, because these two materials have different properties. Same way here, you have one property this way, some set of other properties this way, and the same way this boundary, where the load is, there's a separate set of properties here, that is we call the impedance seen by this wave. Here is different impedance it sees when it's in the medium. So because of that, it will have a reflected wave, right? So that's we call, so there's a forward traveling wave that comes to the interface, and there's a backward traveling wave which is reflected wave, and whatever the left goes in here that's a transmitted wave. So it's very similar to the physics, same concept. So we will define certain parameters around this in the next couple of slides. Now we'll go through an example to make it clear. I want to try cover a few more examples as we go on this course, especially in these new concepts, unlike the previous ones that you have already covered. A length of coaxial line is filled with a dielectric. Length of coaxial line is filled with a dielectric having a relative dielectric cost of 20 and is designed to be 1/4 wavelength long at frequency of 1.85 GHz. So what is the free space wavelength? So free space wavelength, I think it's quite, so the part A, so we know C equals F lambda. They're asking about the lambda, or C of F. C we can take for this as 3 to the power 10 to the power 3 times 10 to the power 8 meters per second, and F is 1850. Now 1850 is in megahertz, so that means 10 to the power 6 because it needs to be in hertz, and that should give you something around 0.162 meters. So that's in meters. So that's the wavelength. That means for that wave to go from, so let's say from peak to peak, if you measure for that wave in the free space, the voltage peak to the voltage peak, that is about 16.2 centimeters away. So if you take a probe and measure voltage along that wave, you will see a maximum here and then a minimum halfway there, which is 8.1 centimeters, and then maximum again full wavelength away 60 points. That's what it means. Okay, so that's the wavelength in the free space. So what is the wavelength in signal in the dielectric field coaxial line? So that is, so basically they are asking the wavelength of the guided wave. Now we know that it's VP or F. Now the problem is, how do we find VP, right? So we have, what we have is VP is 1 over epsilon mu, right? Now we know that this for this particular relative dielectric constant is 20. So what it says is epsilon r is 20. So we can find epsilon by epsilon r epsilon naught. Okay, so that means we can have VP as 1 over epsilon r epsilon naught, and then mu, I can keep it as mu naught because mu r for this material is 1, because usually if they don't say it, you can treat it as 1, because all of these material are not magnetic. Their permeabilities will be, relative permeability will be 1 all the time. So this VP tells you epsilon r, I'm just rearranging that, mu naught epsilon naught. Now this part is same as C. If you remember from the previous slide, the C, I wrote it somewhere as our, yeah, so where did I write it? I may have not written it, but C is given by mu naught epsilon naught mu naught. That's, so if you find the epsilon naught value, mu naught value, which is given, and then do that, you will get something like 2.99 something 10 to the power 8. So now this tells you VP is C over root epsilon r. Okay, now, so if I sub it in here, instead of VP, I can do C epsilon r root F. Now you remember C over F, which you found here, is 0.162. And then epsilon r is square root of 20. Now if you find that, and you'll get something about 3.62 centimeters. Okay, so that's the guided wavelength. So now if you look at this, in the free space, it's 16.2 centimeters. In the medium, in the coaxial line, it's only 3.62 centimeters. Therefore, we can say that in a medium, the wave will always have a shorter wavelength as long as it has a dielectric constant higher than 1, because relative permittivity higher than 1. So that's always the case, because if you see the VP, you'll notice that this is going to be more than 1 all the time, so that the VP has to be smaller. So VP is smaller, then this whole term would be smaller than, or even in here you can say small whole term would be smaller than COF. So therefore, that's the wavelength of the signal in the line. So it also says part C, how long is the line? Now, if you read the question again, a length of the coaxial line is filled with dielectric, having a relative dielectric constant of 20, and is decided to be 1/4 wavelength. So we know that is a full wavelength. So 1/4 would be 3.62 centimeters. So that's roughly about 9 millimeters. So that's the length of that line. So this is an example of using what you've learned before. Okay, so we'll move on to the next one. Okay, so there's few things that we need to understand when we do especially IC designs or even circuit designs. So depending on the size of the element, when I say element compared to the wavelength, so the structure compared to the wavelength, we call this an electrical length. So we define a parameter called L over lambda, as you say here, and that's the electrical length. So L is the length of the structure. So for example, in your circuit, if you have an IC that has a length, that's the length of the maximum dimension of that IC. Lambda, as you know, is the wavelength. Okay. Now it could be the wavelength in the free space, it could be the wavelength in the guided media. Now if this IC is on a circuit PCB, the IC, we have to look at the lambda guided. Okay. Now there is different, so we try to look at this ratio, which we call the electrical length. Now this electrical length is significantly smaller than 1. That means the length of the structure is significantly smaller than the lambda. Or even, so for example, when you do, let's ignore lambda g, we'll just take lambda. The sigma is significantly smaller. We can treat these individual structures as lumped parameters. When I said lumped parameters, well, I'm talking about, inductors or capacitors, things like that. Now, for example, if you look at the frequency 100 megahertz or even 1 gigahertz, but you notice the wavelength, the free space is 30 centimeters. Now, 30 centimeters is a much larger value than dimensions of the IC, which could be few millimeters. So when the IC is about few millimeters, say 3 millimeter IC, and your wavelength is 30 centimeters, even if it's a guided wavelength, could be like 20 centimeters. But you notice in the wavelength, compared to the wavelength, let's say that's 30 centimeters, the IC dimension is too small. It's like, 1/3 at 1 gigahertz. So the voltage variation along the IC is negligible. If the IC is quite large, you can see at one point of the IC you have one voltage, and at the end you'll have another voltage. So it's very difficult for such a circuit, like when the IC becomes larger and becomes comparable to the wavelength, to model it as distributed elements, lumped elements. So depending on where you are in the electrical length, if the L is very small, maybe 1/20th or 1/10th, even 1/5 sometimes, you can model things as capacitors, inductors. Now, when you got 10 gigahertz, okay, 3 centimeters, and then you have an IC 3 millimeters, it's still 1/10. So it's okay. But assume you go to 100 gigahertz. So it becomes 3 millimeters. Okay, so 3 millimeters. Now the IC is 3 millimeters. So IC is as long as the wavelength. Now in that case, it becomes very comparable, like L over lambda equals 1. So we have to model it as a distributed parameter circuit, transmission lines, which we will learn in the next couple of slides. And when the wavelength is too high, so we go to 1000 gigahertz, it's like 1 terahertz. So wavelength is 0.3 millimeter. Wavelength is much smaller than the dimensions of the line, of the structure. So in that case, you can have multiple wavelengths in the say. So if you look at the IC, you can have multiple wavelengths within that, and you can't use these lump parameters or distributed parameters in your analysis. So this is studied by classical optics. So we won't cover that. We will cover this during the lecture. Now, Now we come into transmission line theory. So there's something called telegrapher's equations. I suggest you to have a look at it. We are not going to derive telegrapher's equations, but we will be using it. So any transmission line, as is shown here, we can model it as a resistance, series inductance. Now the inductance stores magnetic energy, and the capacitor stores electric energy. So resistance and inductance is in series, and this is conductance, and the capacitance here are in parallel. Now, so any medium can be, any transmission medium can be viewed as a repetition of these along a line. So if you look at a delta Z, assuming this is a direction, and then you can model the voltages along that line, currents in through that lines. And the telegrapher's equation basically says how the voltage is related to the current. So if you take these telegrapher's equations as it is, you just to go on, we are not interested in deriving this, we are interested in the outcome of this. I think that's the main thing that we need to learn. Now, one other thing that I should tell is, in a lossless line, that means resistance and G is 0. Basically, resistance is 0 means there's no losses, so it becomes LNC. So that's the ideal lossless line. Usually, even in copper, a wire, something like that, R and G values are very small. So the conductance and the resistance is quite small. So that means these values are quite small. Just keeping that in mind, we'll go further. So we're trying to find a relationship between VZT at the input voltage and the output. So if you find that after delta Z, then we can, if you know this voltage, we can find this voltage here. If you know this current here, we can find this current here. And if you apply it at each delta Z segment, then you can work out from the input VZ, IZ, we can work out what is V dash Z, V I dash Z at the output. So we're trying to find that out, but in doing so, we will use some of the physics. And our intention, as I said before, is not to go through this physics, but to find the outcome. Now, for a sinusoidal steady state condition with the cosine phases, that means if your signal is in the form of an amplitude E minus J Z. So your signal will have an amplitude. Your signal can be represented by an amplitude and a phasor, J theta Z. So you can find, so this is simply applying at a particular dVz by dZ equals, so this is the resistance, so this is pretty much V equals Ri formula on slope for a small segment. The voltage difference dVz by dZ equals the resistance that it sees, so it's R plus the imaginary part j omega L is the impedance pretty much, times the current. Same way you can find the current times G plus j omega C negative times the voltage. So that's again apply the same formula. So if you get the second differentiation, second derivative of this, it comes in the form as this if you differentiate this by Z again. This gamma is called propagation constants. We can, and the gamma will be actually this term. To make it simpler, we reduce this term to alpha plus j beta, and then we tell this a propagation constant. And I'll tell you'll understand why it is called the propagation constant as we go on. But this is a differential equation, and solutions to this in the form will be in the form of Vz Iz. In the sense that Vz equals V naught plus E minus gamma Z, plus V naught minus E gamma Z. Now what it simply says is that the voltage at any point Z is a function of two terms. And the same way the current at any Z point is a function of two terms. If we know these terms, we can find the voltage at any point. So we need to know Z obviously because we would know Z because we know where we want to find the voltage. We need to know V naught plus, V naught minus, and the gamma. And gamma you can calculate using R, L, G, C, which is, so if you know these parameters for the transmission line, we can calculate gamma. So that way we can find Vz and Iz at any point. Now omega is the omega equals 2 pi f, as you know before. If you know the frequency, you can find omega. Now, one other thing that we should also emphasize is that V naught plus represent the voltage, so forward wave. So we call the forward voltage. So at any interface, if you have transmission medium, there is a V naught plus for the forward, and then I naught plus. And there's a, for the backward wave, there's a V naught minus and I naught minus. So the Vz at any point is a summation of V naught plus and V naught minus with these parameters. So as a function of V naught plus, V naught minus, and gamma and Z. Now if you look at so normally our resistance, we look at V over I, right? So same way we can look at impedance. So impedance will have a resistive part. So that's the real part, and then imaginary part. So we can look at this transmission medium's impedance at any point by looking at the V naught plus or Y naught plus, which you call Z naught impedance. So we can derive this. It's not difficult to do that, but so we will quickly do this. So previously we saw that these two equations from the previous one, and then we know that these are the solutions for Vz and Iz in terms of V naught E minus gamma Iz, V naught minus E gamma Iz. So instead of Vz, I can sub this here. So I will get D or dz V naught plus E minus gamma Z plus, and then I get minus R plus J omega L. Instead of Iz, I can say I naught plus E minus gamma Z plus I naught minus E gamma Z. So when I solve this, so let's solve this. So this is minus gamma V naught plus E minus gamma Z V naught minus E gamma C, and then you have minus R plus J omega L I naught plus E minus gamma C minus R plus J omega L I naught minus E gamma C. Now if you look at this term and this term, this represents the forward wave, and this term and this term represent the backward wave. So if you just look at the forward wave, so we can find so it's minus or cancels out, the ratio V naught plus over I naught plus, so that we can define the impedance for this line. And that's simply V naught divided by naught plus. So you get, cancels this out, R plus j omega L over gamma. Now gamma, as you know from the previous slide, when you find the solution for this, gamma is in the form of that. So gamma itself is so you can simplify this. This simply says that your impedance can be written for that wave can be written, if you know RLGC and the frequency of your operation, you can find the impedance of that transmission line. And you'll also notice that this is only depend on the frequency, it doesn't depend on your distance. So if you know the transmission line properties, it doesn't depend on the distance in this direction. So he said here is the direction, this node is the impedance. So the end result that we ever after is this. That's the impedance of the transmission line. Now we found a few things. I want to also highlight this. Alpha and beta, we call this attenuation constant. This is called the phase constant. These are important parameters to remember. Attenuation constant tells you what are the it tells you what are the losses associated in that transmission line. So if the attenuation constant is 0, that means it doesn't have any losses in that transmission line. The beta tells you the phase constant. That it means for a certain length, how much phase it changes. So if the beta is in radians per meter. So if you know the beta for a transmission line, so for a 1 meter length, if beta is, say, beta is 0.3 or 0.5, let's say, it means, so it's radian per meter, it means the phase of that wave changes by 0.5 radians in that 1 meter length. That's what it simply says, means. So these things might be quite relatively new to you, so but it's okay, you will get used to them as you do more exercises. Now, okay, so that's a summary of things to remember. So we also all went through the gamma. Something you need to remember. Now the exam is going to be open book, and you can take these equations with you. Now the attenuation constants is, so if gamma can also be written as alpha plus j beta, that's the attenuation constant, real part of the gamma. The imaginary part of the gamma would be phase constants. There's another thing that we call the wave number. We won't be using this, but I just listed it for completeness. Now the phase velocity that we talked about before, Vp over, if you guys remember, mu epsilon before, it can also be found with omega over beta, that is 2 pi f over beta, if you know the phase constant. Now the wavelength is 2 pi over lambda. Now gamma, amplitude of the gamma. And for a lossless lines, it turns out that gamma is almost beta because alpha is goes to very small values. So because of that, the lambda is also 2 pi over beta from here to here. You know the impedance, which you already found. So what you need to remember out of this is, most importantly, is this part, this and that. phase velocity. So when you alpha, when you're quite low loss, your alpha is very small compared to beta. So beta dominates, and the k, the wave number, or gamma actually, is mostly dominated by beta values because this is too small, close to zero, and your gamma becomes j beta. Now wave number k is pretty much minus j gamma, which means minus j beta. That gives you minus 1 beta beta. So you know that k is beta actually. Okay. Now what you should do, also other thing you need to remember is alpha is a loss, and we call that loss in meters per meter. So usually you will notice the loss is in decibels per meter when you look at the data sheet. So we'll talk about that in a minute. So that's the dimensions of alpha. So, and the beta is radians per meter. Now, what tend to happen, the gamma, because it's alpha plus j beta, the gamma itself is per meter reading. So propagation constant per meter, but this has an EPers per meter unit, and this has a radians per meter unit. Now EPers per meter, so you can convert EPers to decibels per meter, and it's a simple translation. So basically, 1 EPer is 20 log E, which is 8.6859 dB. So if your loss is 0.1 EPers, so your per meter, then your loss in decibels per meter would be 0.1 times 8.6859, whatever that value is. So that's in decibels per meter. Because in the data sheets, we will have it in decibels per meter. So if you want to calculate the attenuation constants, you can work backwards. Okay, so as an example, a transmission line is 10 centimeters long, and at the operating frequency, the phase constant beta is 30 per meter, and the wavelength is 40 centimeters. What is the electrical length of the line? So the beta simply says, so for a meter length, it changes its phase. Its phase change is 30 radian. That's what it means, simply says. Now the line is 10 centimeters long, right? So that so beta L should give you the phase change along that line in terms of radians. So that means beta is 30 per meter, and the length is 10 centimeters. So that's 10 divided by 100. So 3 radians is what you will get along that 10 centimeter line. So if you have a 10 centimeter line, you have a 3 radian difference. Now, when you define electrical length, so electrical length is basically the length of that line in the free space, which is lambda usually, is 2 pi, right? So in the terms of radians. Now this length, the electrical length here, which is beta L, electrical length is equal to 3 radians. Therefore, we can say that electrical length in terms of lambda equals 3 radians divided by 2 pi. Therefore, EL is 3 over 2 pi times lambda. So when you That's 4.477 lambda. So electrical length is about 0.477 lambda, or in terms of radians, it's 3 radians. Okay, so just go through these examples. The examples are there for you to understand the concept more. Now we've done that. So the next example, a transmission line has the following RLCG parameters. R 100 ohms per meter, L, G, and C. Consider traveling wave on the transmission line with a frequency of 2 GHz. This is quite a straightforward, because you will have to. So the attenuation constant is gamma alpha plus j beta, but that is R plus j omega L, G plus j omega C. Now R given, L given, GC given. Now omega is 2 pi f. 2 pi times f is 2 gigahertz, so 10 to the power 9, right? So you know all the values, you can substitute that, because you have to get a square root of a complex number. You may, if you have MATLAB, I think I suggest you guys use it, and then you'll get an answer for gamma. And the answer you will probably get is about 17.9 plus 51.85 J per meter. So that's the attenuation cost. Sorry, that's the alpha. No, so that's the complex propagation constant. Now this is alpha, and that's beta. So alpha would be 17.9, which is part A. Part B, the phase constant would be that. Now the phase velocity, Vp, is 2 pi f over beta, or omega over beta. And then because you know omega, that 2 pi 2 to the power 10 9 divided by 51.85, you'll get 2.4 times 10 to the power 8 meters per second. Now that's obviously smaller than the speed of light, because that's in a medium. So that's the phase velocity. So that's part C. Part D, what is the characteristics impedance of the line? So that is asking about Z naught. So it's R plus j omega L over G plus j omega C, or you can also say R plus j omega L divided by gamma, because you already know the gamma. So you can sub these values, and again it's a complex number divided by complex number. You can either use MATLAB, or you can change this to phases and then work it out. But okay, this is much easier, but this one, when you do MATLAB, it's easier. But if you use calculator, you will have to convert that to phases and go through basic mathematics to find the square root of a complex number. Now when you do this, you will get Z naught as 17.9 plus 4.3 J ohms. So that's the direct substitution for the equations that was given before. So let's go to the next example. A transmission line has an attenuation of 10 dB per meter and a phase constant of 50 radians per meter at 2 gigahertz. What is the complex propagation constant of the transmission line? So that's asking about gamma. So it is alpha plus j beta. So beta is already given. The alpha is not given because this is in dB per meter. So we've seen that 1 nepers per meter equals 8.6859 dB per meter. So now it's 10 dB per meter. So we can find how many NEPAs per meter. So NEPAs per meter would be 10 divided by 8.6859, and then you will get X as 1.151 NEPAs per meter. So your gamma would be 1.151 plus 50 J. That's your complex propagation constant. If the capacitance of the line is 100 picofarad per meter and the conductive loss is 0, so it's basically saying what is the characteristic impedance of the line. So characteristic impedance of the line, so this is saying G is 0 and C is 100 picofarad per meter. So you know the Z0 is R plus J omega C divided square root R plus J omega C divided by gamma. Now in this case we don't know the resistance, but we can work this out in a different way. Sorry.